Welcome back for the last video in our module on BLAST. In this video, we're going to walk through implementing the reciprocal best BLAST strategy that I talked about in the previous video. That is a way to define sets of orthologs. So in this homework assignment, we're going to try to define the complete set of putative orthologs between these three beetles. These happen to be the three best annotated beetles. This is Tribolium castaneum is the one that my lab works on. So the first thing that you'll need to do is to follow these links. So if you click on that link, it will take you to this link right here. It will take you to the NCBI website. Once you get to that page, you'll see a download button. If you click on that download button, it should bring up this sort of pop-up menu, and you're going to want to get the RefSeq only and the protein set. Okay. So I think by default, probably the genome sequence is also selected. You don't need that. So once you've got those two things set, then you'll hit the download button here, and it will take this zip file, and probably by default we'll put that in your downloads folder. You can, so that will come as just a regular .zip. You can just double click that on your computer, and it will give you a folder that has a bunch of files in it. You're looking for this one. It's a little bit buried, called protein.faa. Now, I recommend that once you've unpacked that and you've got the protein.faa, you rename that according to the species that you just downloaded, right? Because there's nothing in this download that is super obvious to say this is actually the Anaplophora protein set. So what I've done here, for example, and I'll use these file names throughout this walkthrough, is I renamed protein.faa as AGLA 2.0. 2.0 is the annotation version. Underscore prot, just as an easy reminder that to me that these are the protein files, not the RNA files or the DNA files, and then keeping that extension FAA. So you'll have to do that for all three of the species. So that was the longhorn beetle. Then you'll do that for Leptinotarsa, the Colorado potato beetle, and finally for red flower beetle, Tribolium castaneum. Exactly the same process. You'll get to a page like this for each of those, download, and so on. Just name them something different, obviously. Once you have those downloaded to your local computer, you're going to want to upload them to Bridges-2. So I've given you the link here in case you don't remember it, ondemand.bridges2.psc.edu. That will take you to the Bridges-2 on-demand login. And once you're there, hopefully you know how to do this. This is exactly the same steps as we did for muscle. You've already had to do this in the alignment module. I recommend that you create a new directory because we're going to end up with quite a few files. So rather than mess up your home directory, I've created a folder here called BLAST. So you can just use the make a new directory button there, and it'll ask you to name it. And here I've already navigated. You can tell by the highlighting that this is in the BLAST directory, and I've uploaded all three of my protein files that I downloaded from NCBI. Okay, and I just highlighted here so you can see I'm in my home directory, created the BLAST directory, and then that's where my protein files are. Once you have those uploaded, the first step, before we can BLAST anything, we need to create BLAST databases. So those protein files we need to turn them into blastable databases. So the BLAST software will do that for us. Before we run anything though, remember we don't want to do any computing on the login node. So you can see here I'm logged into, it tells me I'm on a login node. So I'm just going to type interact and start an interact session so that we can create these databases. So once you've started your interact session, you're going to do load the BLAST module. So high performance computing often has pre-built modules that are optimized to use their resources. We didn't have to do this for Muscle because we actually uploaded Muscle onto Bridges-2, so we sort of brought the software with us that we wanted to run. In this case, BLAST is already optimized to run on Bridges-2, but we have to load that module. So at the command line, you'll run module load BLAST, and the capitalization here is important. BLAST has to be in all caps. And then you want to cd into the directory where your data is located. So once you're in that directory, so in my example, I would navigate to the BLAST directory. I just backed up there in the slides. And so now I'm in the directory where my protein files are, and I'm going to run this make blast db. Oh, that should say make blast db. I will fix that before I upload these slides. It's correct down here. It should say make blast db. So at the command line, make blast db -in, and the file name here is the name of one of your protein files. So to keep the example going, AGLA 2.0 underscore prot.faa would go right there where the file name is, -db type, and prot is just telling the BLAST software that this is a protein database. Right? So you just type that in, hit enter, and you should see something like this happen, right? So here you can see I'm in an interact session, not on the login node. You can tell because the machine name here, which is what's after the @ symbol, says R001. So I'm on one of the production nodes, 001. And in the directory called BLAST, I ran this command blast db -in, my file name, db type, prot. Okay, and then this happened. It just spit back at me some of the default output and how long it took to create that database. The result of that, so here I've done LL, which is just a shortcut for ls-l. And you can see that now I no longer have only 3 files there, right? I started out with just my 3 protein files, but now BLASTDB created 7 more index files. And this is what BLAST really needs in order to be able to search. So all of the stuff we talked about in the BLAST heuristic, sort of the first video in this module, that is created, the index files for that are created by this make blast db. Once you've done this for all 3 of the species, you should exit your interact session by just typing exit, and that will end the interact. And that way we're not being charged additional HPC credits when we don't need to be. So we're not actually going to run the BLAST itself in an interact session. This is where we learn how to submit a job to the job schedule called slurm. So all high performance computing centers that are publicly accessible anyway, And usually if you have that much compute resource, you have lots and lots of users. So you have to have a way to schedule jobs, like who gets to run at what time on what resource. And that's handled by this software called slurm. This picture is an example of a job script, and we're going to walk through this in just a second. But this top section that's kind of in purple are the called sbatch commands. You can see they start with sbatch, and these are configuring the HPC resources that we want to use. And then there's a comment line here that sort of separates my sbatch configuration from the actual commands that I want this script to run. So first, when I submit this, it will ask for these resources. When those resources become available, it will start my job, and then it will run whatever lines I have down here. In this case, it will module load blast, and then it will run 2 blast jobs. So let's take a little bit closer look at what's going on here. Obviously, if you're going to ask for some HPC resources, you need to know something about the machines. So go back to module 3 when we talked about HPCs. I had this slide about Bridges-2 that talks about the 3 different kinds of nodes that are available on Bridges-2. It's even more complicated than I talked about at that point, because even within the regular memory nodes, there are 3 types of RM node partitions. There's the regular one. There's also one called RM shared and one called RM 512. The 512 has more than twice the RAM per node, right? So kind of talked about those, but you'll see on the next slide that we have to specify not only sort of which kind of node, but also which partition we want to run on. This table just one-stop shop, I guess, to show you that there are several options among the sbatch. Actually, there are more than this. These are just the most commonly used ones. And let's take a look at how these are implemented. So this is the same text as I had on that slide a couple slides ago. So this slide, right? So I'm just blowing this up so that we can look at it piece by piece. The first 3 lines here are specifying the job name and the standard output and the error file, just the file names. So these are going to help. This is what Bridges-2 is going to refer to our job as. It will also give it a unique job ID, but especially these names, it's important to name them something meaningful, because if a job fails and you're not sure why, these 2 files will give you lots of information to help try to diagnose why it failed. So that's the first place to look if you get a job that fails. This 4th line is where we designate the partition. So -P stands for partition. And like I said, we're going to use the regular memory, just the default partition. On the RM partition, the default node count is 1. So you can think of this, right? Like we're just going to ask for one unit or 1 blade in the RM node in Pittsburgh. On those nodes, you can run up to 128 parallel tasks. Let me back up here, right? So each node has 64 cores. They're dual threaded, so there's a potential for 128 threads on each node. So that's where I get that 128. And so I've also highlighted it here So one node, the max core count here is 128, and that's a little bit deceptive the way this table has it, which is why I just wanted to point it out that this is really threads. There are only 64 physical cores. Okay, but bottom line, what we care about is the number here gives you some idea about how parallel we can run a job. BLAST is very highly parallelizable, right? Because we can split the job and our database can be searched. Like, let's say we have 1,000 genes that we want to blast against our database. Well, we don't need to wait and do those genes one at a time because they don't affect each other. We could, for however many parallel tasks we can run, right? So one way to think about this, we could run 128 genes at a time and search all of them simultaneously. So this is where we get most of our benefit over, say, just running this on our local computer. The next line down is the time. So this is the maximum time that we want to let the job run. So we're starting with the default here of 1 hour. The longer you request, the longer you might have to sit and wait in line before your job starts. So that's one factor that determines how long you want to ask for. But the more important thing is you need to ask for enough time so that your job will finish. Because if your job doesn't finish and the time runs out, it just stops. It doesn't matter where it is in the process, it just ends your job. So estimating time can be kind of a trial and error process, like how long you've never done this before, you don't have any idea how long is this job going to take. So there are sort of two options in practice. One, you can take a subset of your data. So if I've got a protein file that is 20,000 genes long, just take a few thousand of those and run a blast and see how long it takes. The other option is you can just request the maximum amount of time. On the RM partition, 48 hours is the longest that you can ask for. You won't get charged for 48 hours worth of credits. You'll only get charged for however long it takes the job to run. So if the job ends in 30 minutes, even though you asked for 48 hours, you're only going to get charged for those 30 minutes. But this gets back to, if you request a longer period, you might wait in line for a long time before your job starts. So if you ask for 48 hours, expect that the job might not start for several hours before it because for your job to start, it's going to have to wait and reserve those resources. That node in Pittsburgh has to be free for the next 48 hours. And so it's going to take a while before you're going to have a lower priority than somebody who asks for half an hour, for example. And that's really what the whole slurm job manager is meant to do. It weights by how much the user has, particular user has been using, by how much time they're asking for, by how many nodes they want. So for example, I didn't highlight this, but we could ask for multiple nodes. Now this is another level of parallelization, right? If I had a way to, and there are ways that you could split your job to run across multiple nodes. So now we're not limited to 128 threads. We could ask for 2 nodes, and then we've got what, 256 parallel tasks we could run. Right, so you could really massively speed that up, keeping in mind that you're being charged per node. So 1 node for 1 hour is 1 unit. 2 nodes for 1 hour is 2 units. So those multiply. And last thing on this slide, just a warning that BLAST won't tell you if it didn't really finish. And so what you end up with is a truncated result file, and you don't know it's truncated. It just didn't finish, so you have incomplete results, and you may not know if you're not paying attention. So how might you know if you are paying attention is these last 2 lines let you specify your email address and then what type of notifications you want. I always leave this set to mail type all. That way it tells me when it begins, when it ends, if it fails. If you only wanted to know when it ended, for example, you could do mail type end, but I don't see any reason for that. I like to know anytime something happens with my job. And so if your job times out before it finishes, you'll get a different kind of message. You won't get one that says completed. You'll get one that says timed out or failed, like yeah, depending on how it exits. If you follow through this example and you request 1 hour here, I changed it to 2. That's just a typo. 1 hour will be enough to run 2 of the protein blasts, as I'm going to show here in a second. So that you don't have to worry about it timing out if you request 1 hour. As long as you're following the example right here, right? So you could run these 2 jobs, no problem. If you're requesting num threads 128, and I'll get to what these mean in a second, this won't time out in an hour. It will finish well before an hour is over. Okay, so in our job submission script, that's the top half. We've got all our resources specified. Don't forget to add module load blast. And then the last 2 things here are the actual blast commands. So let's talk about those. What's going on with your blast commands? So each blast is 1 line in that last section of the blast, the SBAT script. Here I've given you a link to the NCBI blast command line user guide. You won't need to go to that, but if you do want to look at what are the other options, there's a link to get there. So I've kind of color coded this. This slide is kind of busy, I realize, but the idea here is that we have a query in blue, which is species A, and we're going to blast that against the database for species B. So you sometimes see query versus subject or query versus target. The terminology is the same. This is the generic format of the command. And again, this should be 1 line. It's just wrapping because it doesn't all fit, at least at a font size that you can read. And then num threads here, you saw in my example, I had 128 because that's how many parallel tasks we can run. You get diminishing returns with BLAST on this, just from my own experience, but might as well use as many as we can. So here's an example, the one from the picture that I had here, right? So these 2 lines are here. So BLAST P, the query, is our Castanium prot.faa, and our subject target is HW2 protein.faa. Now, the output format 6 is tabular, and I'll show you in a second what that looks like. So I'm telling it to give me tabular output, so it's tab delimited. The query sequence ID in the first column, then the subject sequence ID in the second column, and then the E value. So this is specifying the output of my BLAST result. And again, if you want to go look at more options, just have a link up there to the user guide. The maximum target sequences to retain, that is a 1, because I'm really only interested in the top hit. It will still retain multiple segment pairs. Like if you get multiple hits to the same gene, those still get retained. But this at least will limit our BLAST result, because at the end of the day, we're only interested in the reciprocal best hits. So it doesn't make sense to keep hits that are lower down. Yeah. Number of threads, 128, and then -out is to name your output file. And again, here's one where you need to name it something meaningful. In this case, we have Castanium at TCAS as the query and AGLA as the subject. And then down below, don't forget when you're modifying your commands here, when you switch the query and the subject, to switch your output file too. Otherwise, this gets overwritten. In the past, this is a relatively common source of error, is that people forget to change the output file name, and so they end up not having what they thought they did in their result file. Okay, so after you've basically typed in a job script like this, and you can do this on your local computer in a text editor and then just save it on your local machine and then move it over to Bridges, because you're going to want this text file in the same folder with your BLAST databases. Okay, so you move that over, and in here, this is what my command line on Bridges looks like. sbatch is the command that says, okay, I'm giving you a slurm command file or job file, and I've got it named tcas versus agla underscore job.sh. That's just what I saved my job script as. And you just get this notice that you submitted a batch job, and it, like I said, it assigns a unique job identifier, and then you get your command prompt back. If you want to see what's going on with your job, where'd it go, there's a command sq, and if you do sq and then -u and put your PSC username there, it will bring up something like this, showing jobs that you either have. In this case, it's showing that I have a job running. So the ST column is the status column. And you may see other things there. So if it hasn't started yet, it will probably do PD to say that it's pending. Okay. And then once it actually has the resources that you requested, it will move to running. If you ever decide you need to cancel a job, you can do scancel and then type in that number, and it will cancel the job. It will, whether it's running or not, it will kill that job, take it out of the queue. There are several other commands that you can use to do job manipulation. Remember back at the beginning of the semester, we did job control for your local Linux. There are basically all those equivalents built into slurm. And if you ever need them, they're easy to Google. Just ask Google what sbatch commands are for whatever you think you want to do. These are the three most common ones, especially SQ if you're wondering what's going on with your job. Okay, so once you've done that, and again, this is the generic form of those two blast commands. I just haven't filled the file names in because my point here is that you're going to need to do this for all 6 of the comparisons, right? So the one I just showed was TCAS to AGLA, and that was 2 jobs, 2 blast jobs, right? You're going to have to do the same thing for AGLA versus LDEC here. And then one more time for LDEC versus TCAS. So you need to do all 6 of those blast jobs. Now I recommend, I just showed you, I did 2 of them in one job script. So just to save some time, an efficient way to do this, and this is again some trial and error, is that if you split it into 3 jobs where each one has 2 blast P commands. So that's right. My job script here has 2 blast P commands. So I've done both directions of TCAS versus AGLA. So I would just modify this to do, say, AGLA versus LDEC and LDEC versus AGLA in a second job script, and then finally, do the 3rd comparison there. Okay. So you should end up with 6 results there, 1 for each of the arrows in this little cartoon. What they look like, so that format in the blast command, we have the query ID, the subject ID, and the E value. So these are my 2 results files, or really it's just a copy paste off the top of it. This is thousands of lines long in the real file. Perhaps the most challenging part of this assignment is going to be you need to now parse through these files and find the reciprocal best hits. So I've highlighted one here, so just to make clear, hopefully, what do we mean by a reciprocal best hit? So when we blasted TCAS against the AGLA database, this TCAS gene, the best hit was this AGLA gene. So we need to then say, okay, for this AGLA gene, if we go over here where we blasted AGLA against the TCAS database, is that AGLA gene hitting the same one in TCAS? So then this gene right here is the same as that one. So this is indeed a reciprocal best hit. Both directions that we did the blast, we got the same best match. You don't need to do anything with the E values. Okay, you're just writing a Python script to do that parsing. The last step is once you've done that 2-way, and so this is the one, the box on the left over here is the result of 2-way AGLA versus TCAS. So going back, right, this I defined because of the matching. This is a reciprocal best hit between AGLA and TCAS. So if I come over here, right, that's in my results for AGLA versus TCAS. So what we need to do is then take that TCAS and say, okay, in my TCAS versus LDEC, what was the match? So I get this gene in LDEC. Then I take that to the LDEC versus AGLA and say, okay, that's the match in AGLA. And then finally, does it match back to here? So this is, by traversing this, I've shown that this is a three-way reciprocal best hit. And so my output would be a file with 3 columns in it. And it's got the correct genes from each species in those columns. Okay. One other note, because for this BLAST homework, you're going to need to report the number of proteins in these files. Here in my examples, I've shown you an example where I have this extra row built in, and I just want to note that, like, be sure you're not counting. If you put headers in to keep track of which columns belong to which ones, because obviously you can't tell by looking at the column which species is which. You're going to have to be careful when you write your scripts that you're keeping your column straight and which species is correct for which column. And just the reason I'm highlighting this is it's the most common mistake in previous years is people add an extra row to keep the header straight, and then when they report the number of orthologs, they're off by 1. So there's a Canvas quiz will be due next Tuesday, and it will ask you to report the number of proteins in each of the individual species. So those very first downloads from NCBI, how many proteins are in those files. The number of one-way BLAST hits. So when I did TCAS against AGLA database, how many results were in that file? Similarly, for the 2-way and then the 3-way, you'll be asked just how many are in those files. And for the 2, 3, and 4 here, where you're asking for the number of BLAST hits, each row in that file is a BLAST hit. So you can just count the number of rows, right? That will answer 2, 3, and 4. How many rows are in those output files? It doesn't work like that for number 1 because the protein files have the sequences in them. That's what's actually being used for the searches. Right, so you'll have to remember back to earlier in the semester how you can count the number of proteins that are in a FASTA file, or the number of sequences in a FASTA file. Okay, and then finally, you need to upload your code that you used to get answers for 3 and 4. As always, if you have any questions, feel free to email me or get in contact on Teams. Also, come to office hours or the in-person sessions. There has been plenty of room in those sessions, so feel free to come to that as well. Good luck.